for talk about some areas of work that might be needed, some resources. We'll talk a little bit about how folks might be able to achieve some degree of redundancy absent a failover protocol in DHCPv6. And ultimately, we'll talk a little bit about a real live usage of DHCPv6 today in the form of the DOCSIS specifications. Oh, there you go. We'll absolutely focus on client, server, and relay agents. You know, they are the three main components here to DHCP. Again, very similar to V4. And I do assume that you have some operating knowledge of how DHCPv4 works, and generally what it's used for. So a bit of an overview on some of the standards that we're using here, or we're going to be talking about. We're talking about RFC 3315, which is the core DHCPv6 specification. We'll talk a bit about RFC 3633, which is what we use for prefix delegation, and we'll kind of review some bits about RFC 3736, which is stateless DHCPv6. So this would typically be hand in hand with auto configuration for just kind of for relation's sake here. I'll offer you a link to the working group page for the DC working group. So DHCPv6, generally speaking, we use it for many of the same things that we use DHCPv4 for today. Get address, IPv6 addresses, configuration information, or all the above. One of the things that we do with DHCPv6, which is somewhat analogous to an individual allocation, is we also use it per RFC 3633 to acquire IPv6 prefixes by DHCP. Generally speaking, the behavior is quite similar. However, the mistake is often made that V6. I remember a few years ago, just as an kind of aside, somebody asked me at a cable conference, well, isn't DHCPv6 simply just an upgrade to V4? I guess at the time it was probably a pretty fair question, given perhaps some lack of understanding at the time. But really, it's not. It's very much a different protocol. We use it very similarly, but it is in fact a separate and distinct protocol, and we should look at it as such. So another difference that we have with DHCPv6 is we have another mode of operation. We call it the stateless DHCPv6, which, generally speaking, is something that we don't have in V4 land. And this basically is something that gets coupled with something like auto configuration or static address assignment, where you have an address through some other mechanism like a static assignment or auto configuration, but you still need configuration information. A V6 address alone is just simply not enough to be functional on a V6 network. So in this case, stateless DHCPv6 would be used to acquire things like your DNS server IPv6 addresses, something that would prove to be quite useful. If you ever want to surf the internet, for example. So DHCPv6, we obviously require V6 transport, and as I mentioned earlier, it is simply not an upgrade to DHCPv4. It is very much a different protocol. So in V6, and again, kind of nag you about this. We in V6 land, we listen on port 546 for clients, and servers and relays listen on port 547. Unlike before, we are solely a layer 3 protocol. We kind of highlight here the link local multicast addresses that DHCPv6 clients, servers, and relays will communicate on. So again, as a layer 3 protocol, we have a very strong dependency on some of that low-level fundamental connectivity from a V6 point of view. Link local being what I'm referring to. And of course, relay agents in V6 can forward client requests using unicast addresses, like we do in V4, where you can simply forward them along the multicast groups that we talked about above. That'd be very similar to what you'd see if you were just to kind of propagate and broadcast V6 requests throughout a network. Obviously not, there has some limitations, some challenges there, but certainly something that is viable if you wish to do so. We do have the notion of relay agent chaining. For those of you who are intimate with DHCPv6, oftentimes we'll lose information about various relay agents once they, as they pass through a network. In the case of V6, we have the ability to kind of encapsulate information about each relay agent along the way, depending on how that packet was forwarded. That's a different aspect of V6. If you were to look at in a sniffer trace for a packet that's kind of traversed multiple relays, you would see a fairly large nested series of DHCPv6 messages. We do employ a larger option code space, while there are some similarities with V4, they are encoded using a different technique. We have 16-bit option type codes, and length with variable data payloads. And most of our options are carried. Most of our data is carried in options. Unlike in V4, where we kind of jam things in headers and that sort of thing, V6 is a bit more cleaner from that point of view, and a lot more cleaner from that point of view, or a lot more clean from that point of view. Pardon my lapse of English. So here on this slide, we do a comparison of V6 to V4 messages. As you'll see, there are, for many of the messages, there are very much parallels that you can pull from the V4 space. And then there's some things that are absent, right? So, for example, we don't explicitly have the notion of a NAC. Confirm, we do not have. And relay forward and relay apply messages kind of go back to the point where we talked about nested relay agent information and how we transmit and relay packets from a server to the network, from a client through the network to a server. I kind of won't bore you with a rundown of all these, but for those of you who are familiar with DHCP4, you'll be able to establish some relationships as to from V4 to V6. So the role of routers in a V6 network. So today, when you enable V6 on your laptops, essentially you choose to enable DHCPv4 or use a static address or whatever. In V6, some of the core specifications call for route advertisements to transmit information on the local link that generally instruct DHCPv6 capable clients what to do, right? So particularly what we're talking about here in on this slide here are the M and the O bits, right? I guess in theory and in some cases practice, the M bit is designed to, or was intended to trigger stateful DHCPv6 messaging, whereas the O bit was or is intended to kind of trigger stateless DHCPv6 messaging. We see this in a couple of operating systems, and I can tell you that to kind of point ahead a little bit, from a DOCSIS point of view, we actually leverage and kind of employ this behavior. Windows Vista will also behave this way as well. Macs do not support DHCPv6, and nor does XP, for whatever it's worth. Natively, I should say. I mean, you could probably put Dibbler or something else like that on there, but Vista comes with a Microsoft DHCP client, V6 client, that seems to behave fairly well. So we're not going to get into any more of the behavior of routers here. That's probably a whole other tutorial or a whole other hour and a half or an hour's worth of time that we can look at for another day. So with that, we'll keep chugging along here as far as V6 as it relates to some of the router behavior. So just there is some. I kind of recap here the M and the O bit. I'll kind of omit some of the information about prefix information options that are transmitted down the way. One thing to note is if you send prefix information options down from the northbound router and you have an A bit set and your O bit set to 1 as well, that's the scenario that we talked about earlier, where stateless DHCPv6 would be employed to help the node get the remainder of its configuration information. So in that scenario as well, if you were to statically assign your node an address and it received an obit and you had a properly behaving DHCPv6 client or an IP node, it would do a very similar thing, or it should do a very similar thing. So now, kind of off of the router space, kind of, I really don't want to kind of get tied up in all that business. I want to stay focused on DHCPv6. You'll find here, we're going to get into some of the protocol particulars for DHCPv6. So in V6, we use the notion of a DUID, a DHCP unique identifier. And it was kind of funny. I think on a NANOG mailing list not too long ago, there was actually a debate or a thread about this topic in particular, because a DUID is not the hardware address of the interface where of the client that sent the message. DUID basically takes one of the three formats that you'll see below, which are specified as part of 3315, which some use the hardware address as its basis, but there are derivations to it. And there are a lot of folks out there who use MAC address as an access control mechanism in their networks, whether it be NAC, some form of a network access control service, or even in cable environment where MAC addresses are used to associate attributes and classes of service to subscribers. Folks on the mailing list are like, well, what am I going to do now? I'm kind of missing some information that I need. We'll revisit this later on in the tutorial when we talk a bit about DOCSIS, to talk about how we in the cable industry had kind of addressed this and specified what we needed to kind of support our deployment and run our business. There are two that are link layer based. One is strictly link layer based. The other one is link layer plus time. And of course, we have one that is vendor assigned, which is essentially not based on anything physical pertaining to the device. So to elaborate, we're going to kind of dig into some of the modes of operation for DHCPv6 here. So the most probably relatable mode of operation to everybody in the room is stateful DHCPv6. And essentially, this is the mode of operation for V6 that is very similar to what we use today. And we use this, it's a four-message exchange, solicit, advertise, request, reply. And we use this to obtain not only IP address information, but prefixes as well, in some cases, as well as configuration information. There is a mode of operation in stateful DHCPv6 that, again, is different than that in V4. It's called a rapid commit. And traditionally, we have a four-message exchange, solicit, advertise, request, reply, which is analogous to discover, offer, request, and act in V4. In rapid commit mode, it is a stateful exchange, allowing for the transmission of both address information and configuration information. The only difference being is it's only two messages, so it's a lighter weight exchange. Now, there are side effects to that. One of which we are aware of, which kind of caused us to not look at it, consider this for use as far as DOCSIS deployments are concerned. In our case, if you have multiple DHCP servers that receive that request, they will both reply assuming that they are authoritatively offering that address to the client. So now you have two DHCP servers sitting in the network thinking that they've just assigned an address to the same client. So maybe in your network that's some networks that's not a problem, but in certain networks, having a common understanding of who authoritatively issued the binding or the lease is very important, particularly if conflicts arise at some point. So again, as part of stateful DHCPv6, we transmit configuration information. Some of which we talk about here at the top of this slide, 3646, which is basically DNS server IPv6 address information. And it obviously it's not mandatory. The one thing to take note about as far as DHCPv6 is concerned, and this is more or less an observation, and I think it's not inadvertent, is DHCP servers and clients will rigidly adhere to the optional request option. Unlike some things that we've seen over the years in V4 land. So if If a DHCP server is configured to transmit more options back than a client requests, the extraneous options won't be transmitted back. The fundamental premise here is you're going to ask me for exactly what you want, and I'm going to only give you back what you want and nothing more, right? So that's kind of important, because we've had people ask, well, if I configure it, why don't I just, why doesn't the server just send it? Well, that's a difference, and it's something to be mindful of, particularly on the client implementation side, because you have to make sure that if you are expecting options to be sent down to clients, that you make sure that those clients are asking for them. And again, just kind of a reminder, typically stateful DHCPv6 is triggered when the M or the managed bit in the route advertisement is set to 1. Obviously, you could manually initiate DHCPv6 on the command line, which happens on most Linux platforms, whether it's ISC's DHCPv6 client or even Dibbler on Windows, what have you. So here, kind of a very simple graphical illustration of a DHCP exchange on a flat network. Again, very similar to DHCPv4. Now, that's interesting. So the NANOG folks had asked me to essentially hide all this packet detail, largely to kind of prevent us from having to go look through and do the eye chart thing here live during the tutorial. Apparently, when we converted to PDF, that didn't work out too well. So I'm going to not go through all those packet traces in detail unless there's something I want to call out to your attention that's different in V6 land. So here in this case, you'll notice that this DHCPv6 transaction uses a DUID, and you'll see that it is DUID with the link layer plus time format. And just as an aside, if anybody wants the actual sniffer traces for these, so that you can look at them and take a closer look, I think I have my email address at the back. Feel free to drop me a note, and I'm happy to share those with you. Because I know looking at them like this text format might not be the most usable format. And you'll see that we have an optional request option here, and again, we're explicitly requesting the recursive name server list and the domain search list. So this here, of course, is the solicit, which is originated from the client. Then we have an advertise, which is the response back from the server. And I'm really not going to bore you with walking through every one of these, so I'll kind of cruise through most of them. And then we have request and then reply. Now, as I mentioned earlier, there is a mode of operation that's stateful in nature called rapid commit, but it's a kind of an abbreviated exchange. You'll see that it's essentially a solicit and reply, and it is stateful. So we are exchanging address and configuration information here as part of this exchange. And you'll notice that, where is it? You'll notice at the top of the second column, the client advertises its ability to support rapid commit. An important point to note here about rapid commit, a client can advertise its capability, but it's really up to the server whether or not he wishes to honor that. So if the server basically says, okay, I'm cool with rapid commit, I'm just going to reply back with a reply, we're done. However, if a DHCP server decides that I'm not going to support rapid commit, he can simply reply back with an advertise, and that will, for compliant DHCP clients, that should trigger them to complete the stateful 4-message exchange for DHCPv6. So, kind of an extension to stateful DHCPv6 messaging. This is DHCPv6 in a relayed environment, and I mean, for what it's worth, there are more and more network devices that, if it supports DHCPv6, there are quite a few of them that actually support relay agents now for V6 as part of the base image. For a while there, it was kind of hit or miss, and also a lot of open source implementations, including that from the IC, supports. They provide a relay agent as well. Now, in the back of this deck, I'll provide you with a client, some configuration examples that you could use with the stock ISC DHCPv6 implementation that can give you a base configuration for how you could set up an DHCPv6 and with ISC software. So what you'll see here is we have a solicit that gets triggered by a client. Relay agent will pick it up and perform what will forward as a relay forward message to a DHCP server. Relay reply will go back to the relay agent. We have an advertise back to the client. Again, transmitted by the relay agent. And then we have, similarly, request to the relay agent, relay forward, and then relay reply from the server to the relay agent, resulting in a reply to the client. Again, we have kind of the details of the packets here. You'll notice that kind of halfway down the first column here on the left-hand side, you'll see where you actually start seeing the nesting of the DHCP messages that have been relayed. Very, it seems subtle, but it's a very important thing to note because it is something that if you see enough of these chained together, it'll be kind of eye-popping to some extent. So I'll kind of flip through the rest of these messages. And again, it's still the same exchange. Ultimately, the stateful DHCPv6 in a relayed environment results in solicit, advertise, request, reply being received by the client. So switching gears a bit to stateless DHCPv6, we mentioned earlier that the implication here is that you have a node that has gotten its IPv6 address, generally only its address, from some other source, whether it's a static assignment or other configuration. And in this case, the stateless DHCPv6 exchange is essentially a two-message reply, information request and a reply, which will supply the client with the configuration information it requested in its ORO. And this mode of behavior generally is triggered when the O bit in the router advertisement is set to 1. And we have a graphical representation of the stateless message exchange, assuming kind of somewhat of a flat network. A noticeably smaller message. Again, we're not asking for as much. And there's only two-message exchange. So a little bit about prefix delegation. I probably should have brought this up. Probably should move these up more so behind the stateful DHCPv6 section. Again, as part of a stateful exchange, a client can ask for not only a kind of essentially a unicast address, but also ask for an IAPD or a prefix. And they can be done as part of the same message, generally done as part of the same message. So this isn't implying that that you're forced to have multiple message exchanges to get first the address and then the prefix. You can do this in practice with one message. And again, it's one or more add prefixes, which could be coupled with one or more prefixes as well, which again is somewhat of a different construct or behavior than what we've come to know and love in v4 land. Kind of again rehashing the message flow here. Kind of not going to bore you with the pretty graphic. What you're going to see here on this slide here is again the nested relay message for the nested DHCPv6 relay message, and then off to the second column you'll notice that there is an IA, the identity association for prefix delegation. Ultimately, this will be used to trigger the prefix delegation for the between the client and the server. And then we'll just follow the message flow through. Like I said earlier, same four messages: solicit, advertise, request, reply. And on this last slide here, we actually call out the. Where is it? I'm sorry. On this slide here, we talk about. I should be able to point out to you the prefix that we delegate. The bottom of the left column indicates that we've allocated a /56 of that with that prefix information to this client as part of this exchange. So in v6 we have the ability to transmit information to clients that are generally v6 constructs, right? So we can transmit IANAs, non-temporary addresses. We can transmit temporary addresses as well as prefixes. Essentially, it's under the administrator's control who governs the DHCP server which you'll reply back to, and ultimately the client has to request them. The DHCP server is going to generally behave in a similar manner, but again, it'll be up to the client to kind of request the appropriate information so that it'll go ahead and it'll get provisioned or offered the right kind of address. I don't know if I want to, I kind of outlined on this slide some differences between IANA and IATA. We talked a lot about IAPD. As far as DHCPv6 is concerned, we're just allocating addresses of different types to the client, and they're not necessarily exclusive to one another. Particularly, if you observe on your Mac or your Windows machine, you can have one or more of each of the following types of addresses at any given time. So the DHCP server generally supports being able to do that interaction with clients as well. So renewing and rebinding in DHCPv6, again, a very similar construct and behavior that we come to know of in v4. We have our timers, T1 and T2. We also send down to clients the notion of lifetimes in DHCPv6, because again, we're kind of operating in parity with how IPv6 nodes will behave. You'll see later in the deck how we kind of leverage some of these timers to facilitate and to kind of engineer a redundancy solution for DHCPv6. We're talking about lifetimes. So generally speaking, a v6 node will renew and rebind at T1 and T2, and ultimately when the valid lifetime has kind of presented itself, if nothing has happened from a DHCPv6 point of view to kind of extend the life of that binding, the client has to do just like any other IP node would do, and it has to essentially cease the use of that address. Here are some captures of renew messages. Again, two message exchange, renew and reply, and then ultimately rebind messages here. Two message exchange, rebind and reply. Something else that's worth noting, and again, I'm trying to I call out things in this tutorial for you that I'm pulling from practice, things that I know that are being used in the real world, not only in other types of deployments, particularly in a DOCSIS deployment, and we'll show you how these are leveraged. DHCPv6 preference. DHCPv6 server preference is essentially something that a DHCPv6 server will transmit as part of its advertised back to a client, and it's an indicator of exactly that preference relative to other advertisements that a client may see. And essentially, the 3315 specifies the semantics behind the option. If there's no preference, it's an indicator that the preference is 0. A preference of 255 is essentially the most preferred. It is the highest preference, and anything preference less than 255, there's explicit behavior. There's specified behavior that clients must adhere to as far as waiting for additional responses. The good thing is it's not like the waiting, the specified timers are an eternity, right? Because that would kind of be problematic from a deployment point of view. But I can assure you that this notion of preference is functional, and it actually has utility in a real deployment. So kind of continuing on the notion of things that we've kind of looked at as far as v6 deployments are concerned. V6, the 3315 specifies this notion of reconfigure. Some of you may kind of equate this to force renew in v4 land. I kind of say that I kind of call this the right way to do what we originally had tried to do in v4. And this essentially, the reconfigure behavior is the ability of a DHCP server to essentially remotely affect a client. and affect it in a way where you're basically sending it a reconfigure message and providing that the reconfiguration key authentication protocol has been implemented and everything's passed. You essentially can affect the client and tell it to renew or rebind. And in some environments, very desirable behavior, right? Because once you kind of send some leasing information to a client, you have the probability of essentially losing touch with that client until it reaches its half-life or its renewal timers. And depending on what your kind of tolerance is for that in your deployment and how you use DHCPv6, something like reconfigure could come in awfully handy. Just a side note about this, reconfigure in particular, in my mind, represents an opportunity for us to leverage IPv6. Most of the time when people talk about v6, they say, well, so why should I go to IPv6? How's it going to benefit me? How am I going to make money? And most of the time, people who are kind of knee-deep in all this say, well, your business is going to stay, you're going to have business continuity. I think this is one of those areas technologically that offers us a pretty good opportunity, right? So imagine, if you will, if you can take a lease for an IPv6 client and extend it for a long period of time, longer than normal, than what you normally might. And now you have a lot less activity, a lot less churn, a lot less moving parts kind of and packets flowing through the network. Packets that you normally would have kind of essentially created on the network so that you had constant communication or interaction with your DHCPv6 client. But now imagine, in your network you got lots of nodes, and you kind of give all these nodes an extended lease, and you no longer fear that you'll be able to kind of get back in contact with them in case you need to change some attribute on the client. Instead, you give them an extended lease, and you use DHCPv6 reconfigure whenever you wish to effect some sort of change. This reconfigure will ultimately cause a renewal or rebind, which would then, as part of DHCPv6, would cause the node to update or refresh its parameters. So I look at this as a potential opportunity for us to kind of leverage v6 and some of the things that it brings with it, and this is tied directly to the vastness of the address space. But again, something for folks who either will or are in the midst of planning their v6 deployments, where v6 is a part of that, or DHCPv6 is a part of that. Yeah, so this slide we talked about this already, the particulars of how reconfigure behaves. Vendor options, very interesting aspect of DHCPv6. I found that a lot of DHCPv6 implementations, and there's not all that many of them, leverage vendor information options quite a bit, from a minimalist point of view to very extreme ones. DOCSIS is one of those that we'll talk about shortly, where I'll show you how we've kind of leveraged those vendor information options to, for the benefit of our deployment, and we've kind of used them in a way to kind of make sure that our DHCPv6 clients are sending and able to receive the kinds of information that we need to provision them in v6 mode and operate those devices. Essentially, vendor information options, as part of 3315, give us the option space within the core protocol, where we can actually specify under a unique enterprise ID options that are specific to that enterprise ID. I won't kind of elaborate too much on this because it'll kind of create some discontinuity around what we're going to talk about later. But again, it provides some flexibility, right? So we're talking about essentially vendor options, kind of the ability to leverage vendor options as part of the core protocol. Definitely adds some flexibility, but at the same time, from a purist point of view, represents an opportunity to kind of get a little overzealous, depending on how you look at it. Yeah, so I talk about the misuse, right? So, and again, what we've done, not to kind of talk too much about v4, but very similar constructs have been specified and kind of added to DHCPv4 as well. Okay, so DHCPv4 and v6 coexistence. So, we're kind of at a place now where we're all on the same page, V4, V6, different protocols, different ports, how are they going to, how do we kind of live in a world where they're coexisting with one another, right? I mean, if anybody's seen the, well, actually, this NANOG network is a perfect example, right? We are today in an environment where we have V4 and V6 coexisting, with the exception of people who are running, well, actually, I put it differently. People who are running Windows are actually living in an environment where this is the case, right? Because if I'm not mistaken, stateful DHCPv6 should be functional on this network. So there are coexistence considerations, and I believe there are RFCs out there that kind of talk about this. When you have a kind of an independent V4 transaction and an independent V6 transaction, you get information that potentially conflicts with one another. These are coexistence issues that we need to be aware of as we deploy IPv6 and want to leverage DHCPv6. Things like DNS server IP addresses, DNS search paths, and that sort of thing. This extends further into how you want to deploy it. So, for example, there are DHCP server implementations out there where V4 and V6 are part of the same binary, and ultimately the same process within the system. Others basically allow you to run two separate and distinct processes, one for V4, one for V6. There is no one size or one shoe that fits all, right? Based on your own deployments and your implementations, you're going to have to choose which model works best for you. So some things to consider as part of this, and we actually talked a lot about this internally. Do you stand up? Do you go as extreme as saying I want to stand up separate and distinct infrastructure for DHCPv6, and what are the limitations and side effects of that, all the way to upgrading in place and running DHCPv6, adding or enabling the DHCPv6 functionality within the same binary. So, on one hand, the first hand, if you have separate and distinct infrastructure, the likelihood that you're going to adversely affect your business as usual, your bread and butter, right? Your existing clients that are V4 only, is pretty small. Separate infrastructure, separate processes, DHCPv6 server goes bananas. You're only going to affect IPv6 people that are using DHCPv6. On the flip side of that, you go to the other extreme where you have, the binary and everything, and the processing all in the same physical binary on the same box. The potential that you'll have some sort of misconfiguration or misbehavior in DHCPv6 that again could potentially impact V4 is greater. Again, something to be mindful of. There is potentially happy medium in there. And this is really up to each an individual adopter as to what decision to make about this. I think at this point, at least in broadband environments, when we talk about delegating prefixes, it seems to me that DHCPv6 is really the most common approach to allow for prefix delegation. There are other techniques, kind of involving routers and that sort of thing. But from what we've seen as far as scalability and kind of the ability to kind of do this in a centralized manner, DHCPv6 really offers us the greatest flexibility. But again, different strokes, different folks. So, we talked about this just a minute ago. So there's definitely considerations when it comes to how you want to roll out DHCPv6 if you're going to roll it out at all. Okay, so hopefully this will get a bit more interesting and less dry. One of the things that we don't have technically in DHCPv6 is a redundancy protocol. A lot of folks out there today, some folks, there are drafts out there that specify, a failover behavior for IPv4 or DHCPv4, and there are quite a few DHCPv4 servers that support the same, and it works quite nicely. In V6 today, we don't have a formal specification around how V6 redundancy would work for DHCPv6. There is some talk about potentially encouraging some of this work in the DC working group at ITF, but there's nothing publicly available just yet. I can elaborate for you some of what we're going to do with DHCPv6, because in order for us to go into a production situation where we're using DHCPv6, we have to have some form of redundancy. It's just not an option to not have that. So a few years ago, I put together essentially kind of what I'll call an interim architecture for how we could do DHCPv6 redundancy, and and I'll provide some details behind this in the next few slides. And it's both for unicast allocations as well as prefixes. And the one thing that you'll note about the applicability of prefixes, prefix delegation is ultimately going to, it seems to ultimately is going to push for some kind of proper redundancy protocol right now, because once you start allocating fairly sizable chunks of address space, you need some way to kind of synchronize that between DHCP servers. If for nothing else, to kind of as part of larger systems within service provider networks, there are systems that interact with DHCPv6 or DHCP servers in general that require that information. So having that information available reliably is very important. And like I said, this will become more challenging for us as we kind of move more and more into prefix delegation. So I mean, you can keep this as simple as possible. You could just simply configure overlapping prefixes on one or more DHCPv6 servers and call it a day. And basically, DHCP servers and clients will acquire the addresses, based on a number of variables. What you're going to see here in a bit more detail is something that's kind of an extension to that. We've taken the notion of ranges, which you'll see in some of the configurations here from the IC DHCP server, where we've basically taken unique or split, essentially split prefixes and assigned them to one or more DHCP servers. We leverage the preference option sent down by the DHCP server. So in this model, if you take the most simple model, where you have two DHCPv6 servers, one with the first part of a 64, which would be a 65, and then the second 65 on the second DHCP server. Essentially configure them with, just for simplicity's sake, one with a 0 preference and one with a 255 preference. You essentially have a model now where you have the notion of a primary and a secondary DHCPv6 server. Clients would generally prefer the server that sends the server that sends advertisements with the preference of 255. So over time, you're going to have one server that generally, I guess statistically, it's probably safe to say it's going to carry the bulk of the bindings, because once the client receives that advertisement, he'll then have to he'll complete the exchange with the one DHCP server, which will basically leave somewhat of an imbalance. But generally speaking, not a problem. And one of the things that we noticed about this approach in particular is we had to make it so that the timers, the preferred, the valid, and the T2 timers are actually very close to one another. Not for the protocol behavior between the client servers and relays, but because having those three timers too far apart essentially created a gap or a void in timing where a client would be on the network with an IP address, and if the server that allocated the address went down, there was a point in time where, an extended point in time potentially, where we wouldn't be able to get information about that client anymore from the DHCP server that allocated. So by keeping those timers close together, essentially what we do is we force the client to renew and then ultimately rebind and attempt to acquire a new address from the other operational server very quickly when it can't renew from the server that originally that allocated the original IP address or prefix. That was actually a very important detail that we took a look at, and this seems to kind of help us suppress some of that undesirable behavior from a availability point of view. So what you'll see here is basically some configuration examples, and these should be cut and paste directly into a .com file for the ISC DHCP server. I actually forget what version of the server I used. I think it was 4.1 or 4.0.1, but these are pretty fundamental. So these shouldn't be these should be usable with just about any version. So again, we have a two server model here, and again, this is the one for split ranges. This one here, so you'll notice here that the prefixes are basically two unique ranges, each being a 65 from the same 64, and then this overlapping one is essentially two DHCP servers, same preference, same prefix, same range. Each with different considerations as far as deployment is concerned. I would encourage you to give it a try. I mean, I think at a bare minimum, it'd be kind of cool to give it a whirl. Yeah, go ahead. Uh-huh. Nothing. No, because ultimately what will happen is you'll get, and I got to see if I enable rep commit here. So there's no rep commit on this one. So in that case, so the question was, is there any under the table synchronization that has to require? Everything you see here requires nothing special. It just works the way it is. So what will happen in this case in particular, with the preference being the same, it'll be timing, right? The client's going to get both advertisements back, and he's going to make some decisions based off of behavior that specifies part of 3315 to decide which one he likes better, right? And then he'll go ahead and complete the transaction with one. And there will be no synchronization, right, which is part of the problem, right, which is part of what we hope to, hopefully we can resolve in the not-too-distant future. But there will be no synchronization. In this case, only one of the two servers will have authoritative knowledge of the actual binding itself, unless you use rapid commit, whereas rapid commit, you'd have them both committed at the same time. And then you'd have, I don't want to say a replica, because I don't know if that's accurate, but you'd have essentially a copy. So maybe they're the same. I don't know. But you'd have the data over there as well. So, but they'd be unsynchronized in nature, right? Right. And so and that's part of the rub. That's a good one. So, yeah, okay, right. So in this case in particular, what will happen is if you try to do an allocation, if server B gave out an address X, server A isn't aware that server B gave it out, but he now wants to try to give it out too, and he ultimately does. He says, I'm going to give it to you right over there in row 3. Well, you're going to say, well, I can't do that. You're going to do what all IPDOs do, and you're going to say, oh, look, I did a DAD, and I got an answer for it. I did duplicate address detection. So the DHCP client should do a decline, and then ultimately run through the cycle again and get an address, right? So you're not going to have any predetermined way under the covers with the DHCP server to say, oops, I can't give this one out because I already gave it out. But after the fact, you'll say, well, I got a decline message, which means some other node on the network has that address. So try again. I mean, it's like I said, it's functional. It's not pretty. It's not perfect. Pretty is relative, right? But perfect, indeed, it's not. Right, and this is what we're gonna use something that looks just like this. So some links to resources, which I'm sure you're all aware of. The IC code. I don't know if IC is here or not, but it's kind of been coming around here for the last couple of years. We did some early work with these folks. I did some early work with these folks a couple of years ago on the front end of their V6 implementation. It's definitely come a long way, and it's a good software package. I encourage you to take these configurations and give them a whirl. So here we have a basic configuration for DHCPv6. And I believe this one includes, if you look about 2/3 of the way down the page, some a configuration statement for prefix delegation as well. So we have the first range, which should be just generic stateful DHCPv6, and then we have the second one below, which is individual allocations plus prefix delegation. So I also included the usage here. largely because I know that when I when I struggle to figure out how to start things up, I often say to myself, boy, I wish somebody would just wrote that down and shared it with me on the front end. So I thought I would kind of do that as part of these and make it so that you could literally just, if you wanted to give this a try, you could just cut and paste and hopefully be up and running in a very short period of time. Here we have some client examples. Generally speaking, you don't have to use a configuration file, but if you wanted to instruct a client to do rapid commit, you would put that rapid commit statement into a configuration file and make sure that you told the client where its configuration file is. And each of those examples below basically gives you an explanation of what the client will do in each scenario. Relay agent, and this is the one in particular that I was kind of struggling with, believe it or not. This guy here was, the relay agent I think was something that the IC added after the fact, the relay agent. So when this became available and I wanted to prepare this tutorial for NANOG 45, I wanted to offer you folks really, and those folks back then as well, something that they could like, not have to pay money for. They can go download it off the internet, fire it up, compile it, and give it a try. So I actually went out of my way to make it so that I had a fully open source example of what you could do with DHCPv6, and the relay agent was the last piece that I think the IC added. So I was sure to add this as well as part of the tutorial. So hopefully you'll find it useful. Like I said, I certainly encourage you to give it a try. Okay, so DOCSIS, and then this is kind of like the home stretch for us here. How much time do we have? Oh, we've got some time. Okay, so some generic terminology here. Cable modems, CMTSs. So CMTSs in a cable network generally provide the relay agent functionality. An MTA is the device that provides voice services in a cable network, and a set-top box is a set-top box for video. When we have an MTA or ESTB or an STB that has an E in front of it, it simply implies that it's kind of physically embedded with the cable modem, but still logically two separate devices. In DOCSIS networks, we have MTAs and kind of the cable modem is a prerequisite, right? Cable modem provides the underlying DOCSIS connectivity, which enables the logical device, the MTA or the set-top box behind it, to come online and be provisioned, right? So we have DOCSIS, which is basically the data over cable standard system interface specification. That's a typo. I'll have to fix that one. And that basically defines how DOCSIS devices like cable modems are provisioned on a network. Packet cable, specification that defines how MTAs or voice adapters are provisioned on a network, and other things, not just provisioning, but for the nature of this conversation, DHCP is considered part of provisioning. So we'll kind of leave it at that. DHCP, we've spent about an hour talking about that now, so I think we're pretty clear as to what that is. And TFTP, which is actually quite heavily used in DOCSIS, is the trivial file transfer protocol, and then time of day. This page here is some pointers to the actual specifications for DOCSIS. IPv6, as far as modems are concerned, is supported in both 3.0 and in some 2.0 DOCSIS devices. So we have 2.0 devices that are able to support IPv6, and 3.0 is kind of naturally a part of the 3.0 specifications. And there is kind of reference to lease query RFC at the bottom. There's also a bulk lease query RFC that should be here as well. I think we'll kind of make reference to how that applies here. If not, I'll try to remember to do so before we're finished. So essentially, as part of the DOCSIS specs, both the 3.0 and 2.0 specs, we specify how these devices are going to be provisioned, right? So essentially what that means is, in a nutshell, all the different DHCP options and all the different flows and all the different interactions that have to be in place in order for this modem to come online and allow you to get a data service or a voice service into your house. In DOCSIS, we specify different modes of operation. So, for example, cable modems can operate in IPv4 mode only, IPv6 mode only, dual stack, which is both v4 and v6, or what we call alternate provisioning mode, right? So basically, it's like a fallback mode where you have a modem that tries to come up in IPv6 but fails. So he'll punt and then go to IPv4. So the mechanics of all those modes we'll kind of steer clear of here today, and we'll just talk about how we've implemented V6 into the DOCSIS space so that you can actually see a real live use case for DHCPv6 and DOCSIS, or DHCPv6, I'm sorry. Again, some reference to some other technologies that DOCSIS leverages. We talked about TFTP and TOD, syslog, SNMP is heavily used to kind of manage and monitor devices. And it is important to note that stateful DHCPv6 is required to provision DOCSIS devices in IPv6 mode. So what that says is we do not really have DOCSIS devices that can be provisioned using stateless auto configuration on the cable network. And of course, DHCP4 is that remains generally the same. So in DOCSIS environments, again, we use DHCPv6 to not only acquire individual IP addresses for cable modems for management, but also for anything behind it, assuming it can support it. There will be also we'll also use that to provide IPv6 addresses for unicast addresses as well as prefixes. So again, pointing back to the use of DHCPv6 for prefix delegation, that's what we use it for. That's what we are certainly using it in that capacity. And again, CMTSs are not only our relay agents, but they're also our northbound routers. They provide us with all the kind of the fundamental messaging that we expect to receive from V6 routers. And within DOCSIS, the vendor options that we mentioned earlier, the RFC, the vendor options as specified as part of RFC 3315, we are specifying options under the Enterprise ID 4491. And I'll definitely elaborate on some options that we specified and that we heavily leverage to kind of enable V6 on the DOCSIS side of the house. And here they are. So under 4491, we have a Cable Labs option request option, which is not equal to the core DHCPv6 option request option. It's kind of an option request option that's specific to the Enterprise ID for Cable Labs. We also use vendor options under 4491 to specify TFTP server lists, time of day server lists, syslog server lists, and boot files or configuration files, and other client configuration options. We also have modem capabilities, which are very much DOCSIS constructs, and we also have a device identifier, right? So if you guys think back, to however many slides back, I mentioned to you that in DHCPv6 we have a DUID, and the DUID is essentially generally not a MAC address, right? And it's intended to be used as an opaque value. So what we did as part of making sure that we orchestrated this to support our adoption of V6, we under our own Enterprise ID, we basically specified a device identifier option, which basically contains the 48-bit MAC address of the device. So any device that adheres to the DOCSIS specification, which includes a cable modem or MTAs or set-top boxes or what have you, will contain this information. This is actually very subtle, but it's very important. We leverage this heavily to not only minimize the impact of IPv6 kind of throughout the northbound systems, but also to make sure that we, in the same breath, also kind of have all of the bits on the wire that we need to enable V6 in our environments, right? If we had to change, the model, and this is exactly the thread that happened, I think, on the NANOG list. If we had to change systems and everything around it to now accommodate a DUID, which is not a CH-ADDO or a MAC address, like we had before, the impact arguably would have been a lot more. It would have been a lot larger, frankly. So we took care to make sure that as part of the specification process, DOCSIS devices that were compliant with the spec were sending us all the information that we needed to run our networks. And additionally, the CMTSs in this case will also leverage vendor information options to transmit information about itself. So now, for example, one thing in particular, a CMTS when relay forwarding packets to DHCP server will append information about itself. One thing being its DOCSIS version. The second bullet here, which is the cable modem MAC address, is essentially the equivalent to the remote ID behavior in 3046 that those of you in the cable space may know and love. Again, it's, that's a very core construct of the way that we operate and deliver service on our networks. So again, this picture very similar to the one from before. You have client, in this case, cable modem, relay agent, CMTS, and the server. Similar flow that we saw earlier. Let's see. So this actually came from a cable modem, and I can tell you that because we've specified for the support of reconfigure in cable modems. While the modem advertises support for reconfigure, a rapid commit, you'll also notice in subsequent slides here that we are not in this case using rapid commit. And you'll notice down here we have I think it's just, it's link layer plus time DOID. And the other thing that you should take note of in this slide here is, this is pretty ugly. This sniffer text the text version of the sniffer trace, largely because the sniffer traces, the Wireshark adapters today don't know how to decode the Cable Labs vendor information options. So one of my colleagues in the cable industry and I have been kind of trying to work on a patch that would kind of add this functionality to Wireshark. We're going to need it because it's inevitable that we'll be looking at sniffer traces for DHCPv6 packets, and clearly looking at this mess here is not going to be quite so useful. And I really did leave it in there deliberately to kind of indicate to you that there's still things that we need to do out there as far as tools are concerned. Wireshark is pretty stock for most of us. This is one of those examples where we got to make sure that we've got we augment those tools to support so that they can support, we can use it to support us ourselves in the day to day. So again, kind of not to belabor the flow here, but again, solicit, advertise, request, reply, and all these are generally available as part of the the slide deck that you can download. And next, I'll show you kind of reconfigure in action, and then this is essentially the flow for reconfigure. So in our case, we'll trigger this from a DHCPv6 server. Generally, in our case, unicast to the client or the modem in this case, and subsequent to that, it'll trigger in this case a renewal. So you'll see that the reconfigure message is being sent down, and I actually don't have the header portion of the packet in here. The reconfigure message is being sent down to the client, and followed by the renew message from the same client, and then ultimately reply. So that is the end of the tutorial. That is essentially my overview of DHCPv6 for you and a use case in DOCSIS. Happy to take some questions if anybody has any. By all means, sure. Yeah, probably, yeah. It's probably a good idea.
Thanks very much for this. We don't have any need at the moment for DHCPv6 on our network, but it's very instructive to learn how this is working. Can you tell me in that last slide where the DHCP server wanted to force a given client to reconfigure to come back and ask me again, how does it know which relay agent to send that to? In the DHCPv4 case, generally the relay agent was sort of in the middle of the transaction during the transaction, but afterward the server could forget all about the DHCP relay agent. It was really just the fact that I had given this IP address out to this guy way far away from me.
Yep. So just one point of clarification. In this case, in this example, it was actually unicast from the server to the client. So it wasn't sent to the relay agent. It was sent directly to the modem. And the server knows that because he's got he's looking in his database for, and he has the binding, right? So if you can envision like a user interface where you could look at all the bindings configured in DHCP server and say, oh look, there's an IP address. I'm going to click on it, and then I want to send a reconfigure message to it. So now, assuming that you have connectivity between the server and the client, which you should have, that'll be unicast message. Now there is the ability to send a reconfigure by the relay, and you'll notice that as part of these packets, the server is aware of what the relay agent is, right?
So the server would have to record that and remember it for the...
Yeah, it would. Yeah. Otherwise, otherwise you'd either have to specify it on the fly as a user, or you're simply without the appropriate level of information to leverage reconfigure via relay agent.
Okay. Thank you. And my other question is about prefix allocation. That's as an ISP now, I definitely have to distinguish between regular DSL customers who are just going to be behind a home PAT router and just need one address. But then if they say, oh, well, can you give me several addresses? It becomes a whole thing. Oh, hold on a minute. I'm going to have to give you a statically assigned address. I'm going to have to remember somewhere which subnet you were assigned. I'm going to have to put the static routing into somewhere and redistribute it to somewhere. And it seems that this whole process has been thought about a lot in DHCPv6, that pretty much anybody's going to be able to just give me a little /56 any old time, which is cool. I see how it works in the DHCP server itself. How does it work in the rest of the infrastructure? How does the IP route blah to blah get injected into your routers? That's
a really good question, and it's kind of timely because one of the things that we're working on as part of the working group is there's a relay. It's called the RAN option, and essentially it's an option that it gets transmitted as part of the response back to an IPD. And it's kind of been in the working group for a bit. We had it refreshed in advance of IETF 70 in San Francisco 74, and basically it is an option that specifies that is sent back by the server, detected by the relay agent, and allows for the injection essentially of a route into the relay agent. So the question that you're asking, I think, is, okay, if I'm a home gateway and I've now been delegated the prefix, me learning my default route is not so big of a deal. I can just use router advertisements from my northbound router to do that. But how do I make sure that the rest of the network, the rest of the network knows that that router over there is right. So this RAN option, you should take a look at it. If you want to talk about it later, I can send you a point to it, but it's really for the benefit of everybody. It's a fantastic question. It really it's the enabler that can be used for the initial route injection. So if you also so that solves the first problem, right? How do you create awareness in the network as to where that prefix gets, all the traffic for that prefix gets routed to? The RAN option is kind of the initial, could provide the ability to provide that initial injection of the route. You'll recall subsequently in the deck here we talked about lease query, bulk, as well as RFC 5007 as well as bulk lease query. That mechanism is largely intended to basically allow for a relay agent that was potentially responsible for routing or knowing the last hop route for that prefix to relearn that information if any unforeseen event happens, right? So without kind of getting too deep into cable S things, right? But if you can imagine that you have traffic flowing up from this home network where there's been a prefix delegated, and the upstream router says, I don't know who you are, right? He issues a lease query to a DHCP server and says, do we know anything about this IP space? And leverages lease query to pull in information about that delegated prefix or things associated with that IP address and ultimately delegated prefix to kind of refresh or repopulate routing information. That could provide for that's ultimately a mechanism that could be used to keep it current, to keep it fresh. So there's kind of two bits and there's kind of two pieces in play there, right? There's the initial population, and then there's the subsequent kind of refreshing of information, routing information into the infrastructure.
That's really great. That sounds as if if everything is as automatic as you're describing, that the it could bring down the level of pain, or it could bring down the cost to the end user for getting a delegation, for getting a delegation of anything more than one address.
Yep.
You know, they could make it completely routine.
Well, we don't have, I mean, we had to do this really, right? I mean, the fact of the matter is the whole idea of statically assigning prefixes to users, that's in scale. It's like unrelated, right? They're just completely foreign concepts to one another, right? So now you take V6, where you got this vastness of address space. You take this home networking model, which has been generally kind of related to small businesses, right? I mean, most home users don't get like a /28 assigned to their house, right? They usually get one address. Now you're kind of smashing two worlds together, right? So, you know, and now that the world that you're smashing together with is really big, right? Millions and millions of people who are out there who potentially might want to use, you know, V6 in their home with a home network that's V6. We really did need a way to make sure that we could do that in an automated fashion, and DHCP really fit the bill.
Thank you.
Yeah. So I do have a question for folks. Lot of Mac users out there. I mean, does anybody kind of feel like they're missing DHCPv6 on their Mac? Like, are you kind of jonesing for it, or are you perfectly happy without it?
I know that it didn't give us the DHCP DNS server. DNS server is annoying, but it's not annoying. It makes it non-operational. Okay, right. So
yes, it needs to be in all the operating systems to get deployed for users, because how many users does Comcast have? Let's say 60 million.
Well,
Round number?
yeah,
Just
lot.
guess. You're not a marketing guy.
No, it's publicly available. I mean, data users, it's like something like 15 and change.
15 million. Awesome.
Yeah.
Can you go visit them all, please, and give them DNS server information?
I'd be happy to.
No.
As long as I get paid. As long as I get paid per visit.
Nope. Just on your current salary.
No.
Go fast. Once a week, you have to visit them all.
Yeah.
No, I mean, but seriously, the enterprise I used to work at had 50,000. Well, when I left, it was 300,000 users on the internal network. If they tried to do V6, and there was no DHCPv6 sending down DNS servers and TFTP servers, Pixie boot servers, every other option that I use in DHCP before, I can't visit them all.
Yep.
Fortunately, I can't visit them all anymore at all. But now the new company is like 20,000 people, so still I can't visit them.
No, I'm with you. I mean, that's kind of why I asked the question. I mean, I share a very similar feeling, right? But I mean, I also understand that Apple. I'm not aware of any plans for Apple to put DHCPv6 on a Mac.
Bug James Wood yet?
Yeah.
Number one. Number two, speak up at 6-man in the IETF.
Yeah.
And also, you could mention it on the list.
I've talked to James about it, but really, I think Stuart is ultimately who we need to bring this up with. But it's not just me, though, right? I brought it up. I think it's also all of you.
Sorry, I didn't mean just you and everybody.
Out of curiosity, Kevin Overman, yes. Does anybody know for sure that DHCP is not in Snow Leopard?
No, I don't.
Snow
Anyone?
Leopard will be out quite soon, and I must admit, I have no idea if it's there. I haven't seen any discussion of it. But
Yeah, that'd be a good data point. Anyone? I'm not holding my breath, though. Windows 7 supports it, by the way. Windows 7. I don't know. Yeah. Okay. Well, if there's no additional questions, have a nice day.